Welcome to ArkDesign.ai. Today we're going to hear from John Locke, Senior Research Scientist at Autodesk, about AI-assisted workflows designed to transform sustainable material selection in architecture.
Hello, my name is John. Let's see, I started my career in traditional architectural practice, but for the last 10 years or so, I've been a research scientist with Autodesk. My passion is around developing new software workflows for design, specifically around sustainability and carbon accounting. So first, what is Autodesk research? Our mandate is to explore what's possible in the future for design and make industries. We're usually looking 5 to 10 years out, and we seek to de-risk that future direction by prototyping and testing solutions that can support our customers and the industry as a whole. And we do that by collaborating and partnering with different forward-looking groups and industry, architecture, engineering, construction firms. And oftentimes with fast-moving technology like AI, things are going so crazily, incredibly fast that our work and our ideas actually outpace legal ramifications. So I have to start with this. So I'll spend 10 minutes reading this. Just kidding. I'll flash this really fast, the safe harbor statement to appease, our legal team, just to say that what I say here are forward-looking statements and not roadmap commitments to our products. So I obviously work for a software company, but what I'm talking about today is more around my team's work in research and is not really indicative of any software roadmaps. So when we look forward in the industry, the future of the industries we serve, Autodesk Research sees 8 key research themes shown here. We believe these have the most potential for transformation. I won't go through each of these, but again, as I mentioned, my focus is, and my team is around net zero buildings research, which explores what it would take for buildings to be carbon neutral, carbon negative with regard to climate change, and how design tools can make that happen. So I want to structure this talk today to lead into generative AI by first starting with generative design. I think it's important to show the differences, but convey how architects can learn from each to really create better, higher performing, more sustainable buildings. So you have this spectrum, and I want to demonstrate super quickly 4 examples along this line to convey the trajectory of computational work and hopefully demystify for everyone and provide more nuance and understanding to what some of these topics look like in industry and real world projects. So first, Airbus. We have a very long partnership with Airbus. And the first project we looked at with them addressed the question, how can we change the way we build airplanes, design airplanes? More specifically, the idea was for lighter airplanes to reduce fuel consumption and carbon emissions. So we started this component with a component called the partition here, highlighted in red. And we used generative design to explore thousands of different design options and find the ones that had the lowest weight and the lowest displacement under multiple loads. So basically, what's the strongest and lightest aircraft part you can create? We then selected design for metal 3D printing. But I think in the context of AI, this is a fairly deterministic problem along the kind of Pareto front of optimal designs. There would really be one single design that is the lightest and the strongest. We ultimately selected that one here and built a full-scale partition. While it would be impossible to design and make this with traditional methods, and it would have taken an engineer thousands of hours using their own kind of intuition, this isn't really AI, but it's more detailed, it's more exact, it's more precise, it takes a long time to set up, and you generate a lot of options. So we wanted to, a few years later, we wanted to look at how do we build a more multidimensional computation problem in the AC space that is, that has a more robust design space, if you will. So we're working with Factor OS, they're a modular offsite construction company in the Bay Area. We're working with them on a 300-unit housing development in Oakland. So here the goals are not just weight and strength, but qualitative goals that I think we all care about in AEC around things like habitability and total carbon, as well as things like cost, kind of the hard limits that we work with. So here we're creating a next generation version of generative design to explore a wider design space of possible options, building arrangement, public green space, different building configuration, materials. That all comes together around the sustainability of the project. And again, this is really generating its own data. So kind of every design you see is another piece of data. So you have thousands and thousands of unique designs with machine readable metrics, but it's not really AI because you're kind of explicitly letting the kind of algorithm know what you want to create, right? So still really interesting, and it's still a piece to complement how we approach AI. And this allows us to really think, how do we want to work better? What are the problems we're trying to solve within architecture? How do we explore multi-scale generative design to navigate these complex relationships between, site, building, unit, and construction? So this really allowed us to have a tool. This really allowed us to have a tool to play that. To have real-time embodied carbon data alongside cost data early in the design process. So this is where it starts to transition to AI, where we aren't being super explicit with how pieces come together, but rather we're making relationships between a catalog of building blocks and then training an AI model to make new rules, and so those might be buildings that look kind of weird. They might be, different, but they're still unexpected. They're not necessarily deterministic. And we're able to start to see ways to assist us in designing in ways that we might not have previously considered. So moving along, one aspect of the research was to explore tools to quickly explore site layouts that are more sustainable and more profitable. And we wanted to look at an option, a prototype where AI is a constant companion. What I was mentioning, not this kind of single click, you've got a building, but rather one where you can have a literal conversation with to augment, your own creativity and your own goals for the project. How would that work? How would that look like? So this involved using natural language to input, to allow interactive text to layout functionality. So any user, regardless of their technical expertise, can engage the AI to help with sustainable idea generation. So that's kind of fundamentally opposed to what I described with generative design, where you have to have a level of expertise to even set up the problem statement itself. You have to be an engineer. You have to know, you have to spend a lot of time setting up the model. Here, we're trying to enhance your own creativity, what you know about design, what you're already good at, and leapfrog over those kind of initial technical hurdles. So, for example, you can enter the text, a site with many housing units, and you receive designs with that feature. You can kind of see the kind of difference there. This process is meant to be very interactive. It's using a technique it's called in-painting, where you can erase a portion of the site and request that it be filled with an alternative design with specific features. For example, you could erase the kind of part on the right and enter more sequestered carbon and more units, and you receive design options that kind of show those changes, right? So you can see those kind of more units on the right. So again, that was, and I think what was interesting about that is that was actually kind of came from studying and learning from some of the scientific research, actually from a paper called MarioGPT. And we found that basically tile-based design is applicable to whether you're making video game levels or whether you're making design building units, right? So it's that connection with science and research that I think unlocks a lot of capacity for designers to explore. Things we may have missed or things we might not know about if we're not engaged with the research. So lastly, I'll wrap up and focus on the problem of data a little bit. AI needs it. In the previous examples I've shown, we were using synthetic data, or basically training LLMs using artificially generated data versus real world data. So keep that idea of data in mind, and I'll try not to get too technical with this. But starting with the problem statement, let's say we want to use AI to help us design better wall assemblies for our buildings. So as we know, buildings are made of assemblies. Those assemblies, like this typical wall assembly, are made of materials, individual materials. And each material contains a certain level of embodied carbon, that comes from the extraction, transportation, and manufacturing process of making them, taking raw materials and making them viable. So topic of embodied carbon is very important to us, and we see it as having a big impact in the AEC industry. We also know that low carbon material decisions and developing new material building assemblies are time consuming, costly, takes a lot of expertise to reduce risk and stay within scope. So again, that theme of like avoiding expertise, but getting us to a place where we can make better decisions without, spending a lot of time and having to kind of go through a lot of research, but rather like enhance our creativity, enhance our goals. So what we're looking at is to propose a new workflow to automate and centralize all of that material data and synthesize the viability of choosing materials, low carbon materials specifically, through AI techniques. So we want to, fit in where you're thinking, like y'all mentioned, there's different design stages. Conceptual design stage is a crowded field for AI right now. I think because, you want to learn everything, you want to be empowered to do a lot at that early phase. You don't want to wait till CDs when things are too late. So we're kind of targeting for something like this would be like, before you get too detailed, where you can really weigh the trade-offs in material assemblies. So again, the objective is to help to design better assemblies with new materials. We think AI can help with many of the tasks to do this. But there's a problem. We need reliable data with transparency and traceability when it's used in AI workflows. And simply put, AI models right now are lacking in sufficient context. So much of the challenge for applying language models to a specific task like this then lies in providing sufficient and accurate context. So our approach is to aggregate by bringing in data from multiple sources, building products, assembly drawings, and live design data. And this is really exciting. This is actually a big deal to us because the potential real value that AI can deliver who face the challenge of designing with the new materials. So this could have a major impact on the materials you select, how you pick it. So, you have mentioned knowledge graphs, and I just think I would encourage you to think of the TileGPT example I just showed. Create a site layout with mini parks. You need to convert that natural language phrase into machine readable code, and we do that through the tool on the left, Weaviate. That basically takes all of these data sources and allows us to find information based on meaning rather than exact keywords. So what that means is if you were trying to search like the building code that you have showed and maybe your own specifications for window, you would have to use the exact same keyword. So that kind of limits your ability to understand the relationships. What a vector database allows you to do is to search not only for related meanings, like related assemblies like lintels, glass, mullions, sills, whatever, but also aspects like performance aspects like visibility, daylight, occupant well-being, etc. And the knowledge graph on the right is a way to show those accurate dynamic product searches. So the vectors are the combining lines that allow us to explore around those nodes. And we combine those, and it allows us to link large data sets that we can then query, we can get info from, and use an AI to actually suggest things like assemblies, because it's now all in the same data structure. So what that pipeline looks like, you have data sources. One data source is Materials 2050. I'm sure everybody, on this call has used things like EPDs. When you select a material for your project, it has data, it might have life cycle data. All of that data can be vectorized and kind of run through this pipeline and put into something that you're able to actually query for thousands of different materials. But then you can layer on other data sources. Other data sources that we all know could be existing assembly drawings. Drawings already have a lot of embedded knowledge showing in detail how the materials are assembled, what its individual components are, drywall, studs, insulation, how those go together. The specs provide instructions and performance criteria. So this allows us to really have a framework to agnostically represent assemblies in a more semantic and computable format. Then you combine the graphs and the assembly with the graphs for sustainable material info. And yeah, a lot of stuff going on this slide. But this is basically a prototype that we're working with. We've been testing this and getting feedback from practitioners. So yeah, on the left, you're kind of like, you have a design goal. Could be, hey, I want a low carbon, 1 hour fire rated wall. You're giving it some data sources. It gives you the assembly view, the graph. It can give you the performance metrics and even suggest alternatives because it knows the meaning of what you're asking for. If you're asking for a different carbon, it could find and seek out different kind of low carbon assemblies. It could understand how, those materials go together in an overall wall assembly. So to sum up, what I'm trying to demonstrate here is how AI can begin to link existing data and knowledge with live information without relying on cumbersome expert systems. So data exists everywhere, but it's often not digestible for future decision making. We have these kind of, in architecture, I think we have a lot of rigid, predefined workflows that can make it challenging to really explore design possibilities. So the shift I've been trying to introduce consolidates all of that data. It's kind of simple graphic, but allowing designers to respond dynamically to project requirements, constraints, and real-world factors at the earliest possible stage in the design pipeline. And just to kind of leave with what does that look like? We see that immediate application would be generation of a bill of materials, right? So by translating AI-generated insights directly into BIM elements, like Revit wall types, we can streamline modeling, energy simulation, life cycle assessments. And I think, we're starting to see a compelling shift in how buildings are designed and delivered, moving from reactive problem solving to proactive informed decision-making, which I think is really important to consider for all of us, for architects, to really start with the problem and find the right tools to empower the designer to make better and more informed decisions. So I'll end there. And yeah, thank you for listening.